And it is here, on the southeast side of the Salton Sea, that the San Andreas Fault begins, starting its 800-mile slice through California, all the way up to Cape Mendocino. San Andreas, the world's most famous fault. And what is the most famous earthquake? Probably the San Francisco quake. In 1906, the northern section of the fault broke loose, and seconds, simultaneously. By the time the movement stopped, the ground had been ruptured for 265 miles, and this magnitude 7.9 earthquake had resulted in a northward horizontal movement of up to 20 feet. This violent shaking, along with the outbreak of fires throughout the city, destroyed buildings over a 400-block area. An estimated 5,000 people died during the quake and its aftermath. In 1857, the central section of the fault ruptured at its northern extreme, and the rupture front moved southward for nearly 3 minutes. When movement stopped, the ground had been ruptured for 225 miles. The west side of the fault moved northward as much as 30 feet horizontally. It was a magnitude 8 earthquake. Because the region was only sparsely settled at the time of this quake, the death toll amounted to just 2. But what about the southern section of the San Andreas Fault, extending from Wrightwood through San Bernardino to the Salton Sea? This section of the fault has not triggered a truly large earthquake in historic times, so how can we know when the last big earthquake occurred there, and just how big was it? We can estimate the magnitude and dates of prehistoric earthquakes by examining sediments at fault sites. Ponds receive sand and mud washed in by rain runoff and streams. The sediment settles to the bottom, forming layers, including dead pond vegetation. These layers of sediment may be disturbed by later fault movements. So, if we dig through faulted sediment in a trench, we see that the sediment was deposited in continuous, nearly horizontal layers, with the older, lower layers buried by upper, younger layers. Look at how this fault line has chopped and cut off the horizontal layers of sandstone and brown mudstone. By measuring the distance the layers have moved, we can calculate the magnitude of the ancient earthquake. The larger the movement, the larger the earthquake. So what can this type of analysis tell us about the earthquake history of the southern San Andreas Fault? Well, the last 4 major earthquakes occurred roughly 250 years apart. However, the last of these 4 was more than 310 years ago, roughly around the year 1690. The fault here has accumulated enough stress to move 20 feet, creating a magnitude 7.5 earthquake. If the fault movement continues rupturing northward, it will pass through heavily populated areas like San Bernardino. Another major quake is imminent because this section of the fault last moved in 1812 and retains some 14 feet of unreleased stress. A combined movement of these 2 fault segments will generate a magnitude 7.8 earthquake. And if the movement continues even farther into the Mojave Desert, it will release another 15 feet of accumulated stress. So the combined movement of the 3 segments could trigger a magnitude 8 earthquake. The message given by the rock record is quite sobering. The San Andreas Fault is poised to move. A magnitude 8 earthquake could occur within the city limits of San Bernardino today, or next year, or 30 years from now. When a big earthquake shakes our houses, we feel it directly. But another great concern is the cutting off of our lifelines by the fault movement. The residents of Southern California live on imported water, and the aqueducts that supply this water cross the San Andreas Fault several times. Our natural gas flows through pipelines that cross over the San Andreas Fault. The power lines that deliver electricity to industries and our homes cross over many faults. And we rely on a system of highways that has numerous vulnerable spots where earthquake damage can severely disrupt ground transportation.